yeah, let me talk about our limits in two variables, or same idea. We've got a function that we want to do the limit as we approach a point, ordered pair values. You know, we're used to these, right? And if we, okay, so that's the limit as x approaches 3. We use our little techniques, factoring and so forth. And then we can plug in ultimately. Well, when we go to two values, now that's the limit as x approaches a number. But it's really the limit of a function, right? F of x is x minus 3. As the independent variable or the input values approach 3, because you can't, there's not a value at 3, right? Not a function value at 3 here. But as we approach 3, we can say the limit is 1 over 6. Okay. You will have the same rules. Now, what you the difference is here, we're approaching x approaching 3, so we only have one. We're approaching. We did it. We looked at it graphically, so we're approaching 3 here. So it's basically a one-dimensional. We're approaching that 3. Now, when we go to two variable functions, if you will, we're going to have to look at ordered pairs as we approach whatever. A lot of them will be 0, 0 of this f of x, y function. Okay? And so it gets a little more complicated pretty quickly, as 3 dimensions typically do. Okay? But if we think about it now, instead of approaching one value, now we're approaching a point, but it can approach from any direction of that point. And if we think about, just think about your domain here, the x and the y values. And so we're approaching, in this case, 0, 0. But x, y can approach any way we see fit. And so we can approach here, we can approach here, we can approach here, we can approach here. And it doesn't even have to be straight line. It's in the plane, but I mean it could be approaching, with a parabolic kind of thing. Approach along y equals x squared, right? But there's some things to think about. But there is good news. Okay, so we're kind of approaching. We want to get around 0, 0, close to it, and that's kind of where the real technical definition. You look at it in a small kind of neighborhood of that point and see what your limit is in that particular vicinity. Okay, that's the idea. What happens to the z value for that? Okay. But the good news is, some of the same rules apply. There's a few little tricky ones. But even if we have a scary one like this, I don't know why I picked this one exactly, but just to make a point, I guess. All right, so we've got the limit of x, y approaching 3, 4. Like a lot of them approach 0, 0, but in this case, let's approach 3, 4. Of the cosine of 25 minus x squared y squared minus y squared, square root of that, divided by x minus y. Okay. Looks real scary, but yeah. As long as everything is continuous here, you can just substitute. If the values can be substituted, that's usually the way you go. cosine is continuous at 3, 4. X minus y, that's continuous at 3, 4. Just substitute in, can't we? So we get the cosine of square root of 25 minus 9 minus 16 over 3 minus 4. Cosine of 0 over negative 1. Cosine of 0. Yeah. So we wind up with negative 1 is our value there. So, yeah, nothing. I mean, there's a lot going on there, but it ultimately just winds up being substitute in, plug it in. All right. Now, we also have, if we can, our same little tricks. Because, of course, what will happen is, there's L'Hopital, but there's also the conjugate thing. Here we can't substitute in, but with the square roots, remember we learned about the conjugate there, and so sometimes that can be helpful. Multiply top and bottom by the conjugate of the square root part anyway. So that winds up being the limit as xy approaches 0, 0. X, let's go ahead and factor that out. And then multiply these out. Of course, that'll be x minus y. And then our cancellation. And so now we have, as xy goes to 0, 0, we've got 0. Yeah. 0 plus 0. Over 1, yeah. Okay. So the very same ideas. All right. So multiply by conjugate, factoring, all that still is going to apply here. Now, a couple other things, a little trickier ones. Of course, a lot of times it may not turn out that it exists is part of the problem. For example, the limit as xy approaches 0, 0 of y over x. All right. Well, one thing you can do, since I'm trying to approach this 0, 0, and that's kind of why I went through that business I did at first, we're trying to approach this 0, 0, and there's nothing much we can do with that. So let's think about it for just a second. As we approach, when we say this limit has a value, that means any way we approach it, the value is the same. So if we can find two that aren't the same as we approach in two different directions, if we can find two things that aren't the same, then our limit does not exist. Okay? And so, in this particular case, let's approach it. Yeah, your limit, remember your limit from your right has to match your limit from your left. Well, now the limit from all directions has to be the same. And so it's not a right or left thing, but it could, I guess, be that easy. But let's approach this on two different lines here. Let's approach 0, 0 from the x-axis. which on the x-axis we're talking about the y being 0. And so for our f of xy here is the y over x, right? And so when we approach along the x-axis, we're looking at the y being 0. So we're looking at the fx0, right? And so that would be what? 0 over x? So that, as we approach along the x-axis to 0, 0, the function values are going to 0. Now let's approach. Now, of course, we can't, we're not going to approach from the y-axis because that's not in our domain. Okay. So we're going to approach on another line. Let's approach along the y equals x line. So, yeah. So we're going to approach here. Okay. Well, if y equals x, then what's our function values there? If the y equals x, can we say we're looking at the xx points? Because y equals x? We could do 2x, it'd be the same. And so that would be x over x, which is 1. So the function values there are 1. And so the limit of xy as approach 0, 0, if we approach the from the x equals 0 line, the x-axis, and y equals 0 line, the x-axis, we get the values of this to be 0. If we approach y equals x, we get the value of this to be 1. So the limit as x, y approaches 0, 0 of y over x does not exist. We've got two different values being, and of course, yeah, you could think of other, like I said, you could do y equals 2x. That would approach 0, 0 in a little different way, but you would get 2 there. Yeah. Oh, 3 dimensions? I didn't plot that one out. Well, it just wouldn't exist at 0, 0. I don't know. But let me show you one more. Way out of time, but started a little late today. All right, let me show you one more. One other technique. So find different values. Okay. All right, let's do the limit as x, y approaches 0, 0, x, y, x squared minus y squared over x squared plus y squared. And the one thing we note about that is we can't use our little techniques because that one doesn't factor. Right? So sometimes you can use the squeeze theorem. What we know about this is the values of that, because the numerator is less than the denominator, the biggest we can get out of that is positive 1. And the smallest we can get is negative 1, because of the way this is it. So x squared minus y squared has to, over x squared plus y squared has to be between negative 1 and positive 1, because the numerator and the denominator. All right, well, if we multiply everything by xy, we get minus xy is less than or equal to x squared minus y squared over that times xy. And then that times xy, we get that, okay? Now, if we take the limit as xy approaches 0, 0 of everything, here, here, and here, what's the limit as xy approaches 0, 0 here? That's 0. And that's the limit that we're talking about. There's There's our limit that we're talking about. And this, of course, the limit of that as xy approaches is 0. So we've got this thing trapped between 0 and 0. So what must this be? By the squeeze theorem, the limit as xy approaches 0, 0 must equal 0 by the squeeze theorem, because it's squeezed between two 0 things.